This is going to be a video about the method of undetermined coefficients. This one's going to be a little bit different from some of the other videos that you may have seen of mine. I'm going to use a document that I've already written that goes over undetermined coefficients and kind of walk through some of the steps. My intention around this particular video is that you've actually seen some undetermined coefficients already. And we're going to go over the general ideas and then some decision-making process for how we deal with the coefficients and the functions, and we will do some tricks for what we do at the end. All right, so first one, x double prime minus 3x prime plus 2x equals 0. So you should know how to find a characteristic equation and to find a function that would be a solution to that. It's got two c's because we have a double derivative right there. So we integrate twice, essentially, with our little algebra tricks in order to get the solution to this. That's why we have two c's. So we use undetermined coefficients when we put a function of t on this right-hand side instead of the 0. The most common way to think about it, or one of the more common ways to think about it, is to think about that as a force that's being applied to a system where this is representative of a spring mass system with a damper. This particular problem is not a damper problem because that has a negative there, but we can use that. That's the way that we typically think of these things. So one force in particular, you can see this bump, 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 right? You may have heard me talk about this before, but when I'm driving my car on a road that is made of concrete, at each little intersection or at each little break in the concrete, I get a bump, 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 right? And that could be representative with an impulse force like this. And we have ways to model that in math, but we're not going to do that right now. So that your time axis would be like this, and you would have this bump force, right? So before we go and we start doing those, we got to start with easier ones. So what I have here is x double prime minus 3x prime plus 2x equals t squared. So the force that I'm replacing that 0 with is t squared. And one thing that you should know already is that my solution has two components to it. It has an xc and it has an xp. The easiest way to think about the xc is it's the part that takes care of the two integration constants. No matter what my solution is for this thing, it kind of has to have two properties. It has to have two integration constants, right? It has a c1 and a c2 because it's got a double derivative. And it needs to, so that's this right here, and it needs to fit the differential equation. The way that I've phrased this in the past sometimes is that x double prime minus 3 times the first derivative plus 2 times the function itself needs to, quote, pump out a t squared. So the answer is going to wind up being this thing, and we'll get down there. I'll show you how we're going to get that in a moment. And let's see, what do I want to say about this right here? So if I had 5x equals 10, I need something that plugs through here, that plugs through this x that gives me 10. I think you should say that that's 2, right? But it fits the differential equation. The 2 fits this equation right here in that it, on the left side, if I plug it in, it gives me 10 out. The reason I say that is because this is the same thing here. The left side needs to fit this equation and give me a t squared out. So it's undetermined coefficients because we have these functions with these undetermined coefficients. I have a times t squared plus b times t plus a constant. So what I'd like to talk about with that one, or with that particular equation right here, this xp, is how I decide what I get. So what you need to do is look at your force that's being applied, the t squared, and you need to derive it until it either goes away or it repeats itself. If I were to derive a t squared, it would derive to 2t, and then that would derive to 2. The derivative after that would be 0. That's what I mean by goes away. Derive it enough times that it goes away. So this at squared plus bt plus c If you look underneath of this t squared, it's just a t squared. If you look underneath of the 2t, I just took the function but without the coefficient of 2. And then if you look at this one right here, the 2, it's really just a function of 1 that's been multiplied by 2. So what we do is we put a coefficient that is undetermined, a, on the t squared, b on the t, and c on the 1, which just shows up as a c. Now, this next part you should be familiar with. So I'm going to go through this kind of quickly. You then find your xp. So this is our guess at our xp. We find xp prime. We find xp double prime. Notice this is highlighted in blue. It's going to go in for the blue right there. Notice this one's highlighted in green, goes in for the green. The yellow goes in for the yellow. When we put all those in, we wind up getting this mess. You can see this right here, 2at plus b, is the same as this right here. It's getting multiplied by that -3. So what I do, I plug that all through the differential equation, and I set it equal to t squared. That's going to make it so that this thing fits the differential equation. That's as long as I've guessed the correct at squared plus bt plus c. So you go like this, you set it equal to t squared. We combine like terms, or we multiply out. And then what I want to talk about here is how I've color-coded things. If you look at this, I've got a 2a, a -3b, and a 2c. Those are all the terms that do not have a t or a t squared on them. Notice the orange terms here have t and a t. And then I've got one yellow term right here that has a t squared on it. And that accounts for everything on that left-hand side. And I know that that needs to be equal to t squared. So one key about these coefficients is that they are coefficient numbers. There's no functions in there. There's no time. There's no sine of t. There's no t to the fourth, right? A and B and C are constant numbers. So what I could do is this thing on the right side is t squared. What I can do is write that as 1t squared plus, plus 0t plus 0 times 1. And then what I can do, let's look at the purples first. Actually, we'll look at the yellow first. 2a times t squared. That's the only t squared term. I've got it right here. This 2a has to be equal to the 1. That's what I wrote right here. 2a equals 1. And that gets me to a equals a half. In orange, notice there is no t term on the right-hand side. So what I can do is create a t term by writing that t term as 0 times t, because then it's equivalent to this previous line here. And then I have these two orange terms, this thing times t. So what I get is that -6a plus 2b, that's the coefficient of t on the left side, it has to match the coefficient of t on the right-hand side, which is 0. That's where this equation right here comes from. -6a plus 2b matches this, is equal to 0, matches that. What I can do there is plug in this a value that I know of a half and get b equals 3/2 with some algebra. I'm going to do the same thing with my no t terms. My no t terms are the purple ones, 2a minus 3b plus 2c. Those are all the things that don't have any t coefficients. And it's got a 1 here. So I match them up with what I have having a 1 on the right-hand side, which is a 0. So this has to be equal to 0, just like the previous one. That's the line that I have right here. This is equal to 0. From there, you can plug in the two values that we know and solve for c. And I get c equals 7/4. And a half, 3/2, 7/4. If you come up here, boom, that's my xp. What I know is that this, when pumped through this differential equation right here, it's going to give me t squared as long as I didn't mess up any of my algebra. If I add that to my xc, which is this thing, then it both fits the differential equation and it has the two integrations of the two constant integration constants, which means that it's the solution. There's only one solution to this differential equation, or one general solution to this differential equation, two c's, and it fits the equation. And that's what this thing does when I add those two together. Now, let me scroll down here and show you what I did in purple. So, you should be familiar with using RREF. If I do that on my calculator, what I can do, or what I can do on my calculator is use it to solve linear systems. So what I want you to see, this and this and this, I solved them using algebra here, but oftentimes it's not quite that easy. It's much faster to use our calculator to do it for us. So I've got 2a, and then I've got a blank, and then I've got a blank is equal to 1. That is this equation right here. Next one, I've got negative 6a plus 2b, negative 6a plus 2b, and then a blank is equal to 0. And then I've got the bottom row right here equal to 0 as well. If I turn that into a matrix, let me pause. If I put that into this matrix here, my A column goes along here, 2, negative 6, 2, 2, negative 6, 2. My B column has a 0, and then a 2, and then a negative 3. And notice this is the t squared equation, this is the t equation, and this is the no t equation. So you can see I can pack all this information into a matrix, and then that, take a look at that. I'm going to pop it up in a moment. My calculator, I go into the matrix. You can follow my keystrokes by watching my red button. So I go into the matrix, I go over to edit, hit enter. I make this a 3 by 4, and then I type my numbers in, 2, and then 0, and then 0. I'm going to pause and put it all in so you can do. You can see this matrix here matches the matrix that I have right there. Now what I can do is quit out of here, clear anything I have off. I'm going to go back into the matrix. I'm going to go over to math. I like to go around the top to get to RREF. That's reduced row echelon form. And then I pull up my matrix right here, and I apply that to this thing. And I hit enter, and it gives me this decimal. Now, these decimals aren't that bad, but a lot of times it's so much nicer to give fractions. So I'm going to math frac this thing, because you can do that with a matrix. Math frac the matrix. I get a half, I get 3 halves, and I get 7/4. If you notice, a half, 3 halves, and 7/4. So my general suggestion with these types of problems is to do the work to figure out how to get to this point in the process, and then go ahead and build out a matrix and use the calculator to solve the rest of your problem for you. We're not always going to have ones where I can so easily get A and then use that to get B and then use that to get C. Imagine if there was a number right here. That would suddenly increase the complexity a lot. And using the calculator also allows us to attack forces, inputs, that are much more complicated than just a t squared. So I'm going to do one more video about this. But I hope that this helps you. Oh, I guess I'm not done yet. So what is my x of t? It is this, which is the xp, plus this, which is the xc. Remember, there's 2 super fundamental pieces to this. This plugs through the differential equation to give me, this right here plugs through the differential equation to give me my c's. It gives me 0. And then this piece right here plugs through the differential equation to give me my t squared that I want on the right-hand side. So as a whole, those 2 together become the general solution to that differential equation. But what I was saying a moment ago is that you should be able to set up your equations. You should have some ideas for how to get there. You should be able to get to this point. You should be able to turn that into a matrix, and then you should be able to use the matrix to get your coefficients, and then you should be able to give me your solution like this. So I'm going to do one more video with a handful of other examples that help you see how we get this blue line here. And hopefully you'll have lots of ideas and skills for how to do this. See ya. Bye. Thank you.